Hello, this is Mr. N again, and right now we are going to work on the Chapter 3 AP Calc review. This is the review sheet I have posted on the website, and here is the corresponding video that goes with it. Okay, so let's take a look at this first problem. On this first problem, it says water is flowing out of an inverted cone, the famous cone problems, at a rate of 40 cubic centimeters per second. The height of the cone is 24 centimeters, and the diameter is 12. First, we need to find the rate of change in the height of the cone when the radius is 2 centimeters, and then we need to find the rate of change in the radius of the cone when the radius is 2 centimeters. So let's do each one of these separate, but we will use the same diagram for both. So let's go ahead and draw our givens and list them all. So we are given that we have an inverted cone. So we've got this shape here, and water is flowing out of this at negative 40, and I'm using negative because it's flowing out, cubic centimeters per second. So then we've got water in here at some sort of height, and it tells me that the height of the cone is 24. So this height here is 24 centimeters, and the diameter is 12, which means the radius is 6. So let's go ahead and put that in there. R is 6. So these are all my givens. And I'm also given something else that I should know, and that's the volume of a cone, which is 1/3 pi r squared h. Now, what value is this? Negative 40 cubic centimeters. This is a change in volume, so this is my dV dt. Okay, so we need to find, in this first problem, it's asking us to find the height of the cone, the change in height of the cone. So we need to find the dH dt when the radius is 2 centimeters. So we're also given here, we need all this when r is 2. Now, in class we learned something special about cones. If I were to go ahead and I listed all my givens, my next step is to implicitly differentiate and plug in values. But if I were to implicitly differentiate at this point with this volume formula, I've got two variables here with respect to time. I'd have a dV dt, so we can write it as v prime, like I know some of you like to do that. And in here, I would have to use the product rule. But there is a trick around it with cones, and that trick is to set up similar ratios with similar triangles. So we can set up a ratio with similar triangles, and in this case, let's take a look at what we have. We have this situation. When my triangle has a height of 24, the radius is 6. When it has a height of h, the radius will be r. So I can set up a ratio that says 24 to 6 in terms of height to radius is h to r. In this problem, I want to find a dH dt. So I want to substitute so that this equation only has h's. That's the key here, and it simplifies this problem tremendously. So let's go ahead and solve for r, since I want my problem to only have h's in it. And in this case, I will get r equaling, I can cross multiply and divide 6h over 24. So r is simply going to be h over 4. So now that we have this value of r, I'm going to go ahead and replace that in my volume equation. So my volume ends up being 1/3 pi times this radius, which is h over 4, squared times the h. So I made that little simple substitution, and now this breaks down to be 1 over 48 when I simplify this, pi h cubed. Now I can take the derivative of this volume with respect to time. I will implicitly differentiate. Again, some of you like to write it as v prime. That's fine. You can go ahead and do that. Just understand that it's a rate, and that we're talking in this case with respect to time, not any other variable. So dV dt ends up being 3 over 48, and we can reduce that in a little bit, pi h squared dH dt. Again, we took it implicitly differentiated. We took a derivative of that h, so I need to respect that with time, so I need a dH dt there. Now I pretty much have everything I need. I know that, oh wait, here they tell me when the radius is 2. What's the height when the radius is 2? Well, we have a ratio. We know that 24 over 6 equals h over r, but when my radius is 2, I get 24 over 6 equals h over 2. So that means my height here for this particular problem, cross multiply, reduce, like we do, and the height will be 8. Okay, so we can substitute that in as well. So let's put in everything we know. We know dv dt is going to be our negative 40. Whoops, let me go ahead and put that in here. So let me erase this. Okay, and we're going to say our dv dt is negative 40. I substituted this one right here. And now I'm going to put in the value for h that I found, and I will reduce that. So over here, I end up with dv dt equals this 1/16 pi times my 8 squared dh dt, and I can solve for dh dt, and I end up with negative 10 over pi centimeters per second. Okay, moving on to the second part of this problem, we need to find the rate of change of the radius. This time it's this, so this is a, let's put another color, the rate of change in the radius, and this time this is a dr dt. So it's the same exact problem. Here we have a radius of 2, so all our givens are pretty much the same. The only thing different is when I have my volume equation here, since I want a dr dt, this is what I'm trying to find, I want to just change this h to be in terms of r. So again, we have this formula that we had set up here, my ratio, and we said that 24 to 6 was our h to r, but this time I want to get rid of the h, so let's go ahead and solve for the h. So h is going to end up being 4r. So my volume ends up being 1/3 pi r squared times the 4r. So let's simplify this down a little bit. We get the volume equaling, this is going to be 4/3 pi r cubed. Pretty interesting that it came out to be that formula, don't you think? So let's go ahead and differentiate this implicitly. So we have our dv dt. In fact, let me do something here. Since some of you like to use that v prime, I'll just do this in terms of the v prime. So let me erase what we have there. So we will write it as v prime equaling, oops, I had to erase too much here. So this becomes 4/3 pi r cubed. Okay, so v prime equals 4 pi r squared r prime. Now let's go ahead and substitute in the values we know. This is negative 40 centimeters cubed per second equals 4 pi. They want me to do this when the radius is 2, so 2 squared r prime. R prime is my dr dt, which is what I'm solving for in this. And cleaning this up, you will get this r prime to be equal to negative 40 over 16 pi. And then we can reduce that to say dr dt, our change in radius with respect to time, is negative 5 over 2 pi centimeters per second. Okay, let's go ahead and move on to our next problem. Let me slide this up to here. And in this one, it asks us to implicitly differentiate x cubed plus 2y cubed equals 3xy squared. So I will go ahead and use this one. I'll use the primes in this case. Again, you can say dy dx. So if you choose to say y prime, just understand that this means dy dx in this case, because I'm going to differentiate with respect to x. So if you wouldn't put an x prime, because x prime would just stand for dx dx, which is 1. So we reviewed that in class, so let's just remember that here. Okay, so implicitly differentiate this. So this becomes 3x squared dx dx, right? So, but that goes away, plus 6y squared dy dt, or I'm sorry, dy dx, so we'll put the y prime, equaling, now here I got to use a product rule, and I'm going to say that this 3x is the first one. So 3x, so that's the first, times derivative of the second, which will be times 2y, y prime, plus the second in this case, which is the y squared, times the derivative of this first one, which will be 3x. So this will be, whoops, this should just be a 3 right there. So let's go ahead and fix that, and we will say that this is just 3, no x, okay? Okay, so let's continue on here, and in this case I'm going to combine this over here. Whoops, sorry, this will be 3x squared plus my 6y squared y prime equaling 6xy y prime plus my 3y squared. Now we want to put the y primes all on the same side, so in this case we will end up with 6y squared y prime minus the 6xy y prime, and then everything else, and that means in this case it'll be this one will come over to the other side, so we will subtract that over, so this ends up equaling 3y squared minus the 3x squared. So now we'll factor out this y prime, whoops, wrong tool. We'll factor out this y prime, and we end up with 6y squared minus the 6xy equaling this 3y squared minus the 3x squared. So y prime ends up being 3y squared minus 3x squared all over 6y squared minus 6xy. Now let's see what we can do with this, if we can reduce it down at all. And in this case I could take a 3 out of the top, and I'm left with y squared minus x squared over, I could take a 6 out of the bottom, and I'm going to take a y out, and I'm left with y squared, or I'm sorry, I'm just be left with y minus the x. Now I can factor the top out as well, so y prime ends up being, this is 3, well this will reduce with that, so let's remove this 3 here, we don't need that one, so this ends up equaling this guy will factor into y minus x, y plus x, all over, this is a 2y, and then the y minus the x. So those reduce out. So you end up with y prime, we'll write it down here, as equaling the y plus the x over 2y as our final answer. Okay, now, in the next step, we are asked to find the slope of the tangent or tangent lines to the curve at x equals 2. Now, if you use Desmos, I don't know if you've ever used that before, but try using that, and you can actually plug this whole thing in there, and you'll see what the graph looks like, and you'll be able to see where tangent lines could be for this graph. But we don't have that with this software tool, so I don't have the luxury of showing you that. So let's just go ahead and do this algebraically. But the thing is we're asked to find it at x equals 2, so I need a y value. So at x equals 2, I can come up with a couple different y values. So I'm going to say 2, I'm using my original equation right up here. So I'm using this original one, and I'm going to plug in the 2. So 2 cubed plus 2 times y cubed equals 3 times 2 y squared. Cleaning all this up, I end up with 8 plus 2y cubed equaling my 6y squared. Let's put everything on the same side. So 2y cubed minus 6y squared plus 8 equals 0. Alright, at this point, what do? How do I solve for the y? Well, there are different techniques, but if you want to use your graphing calculator and just imagine these as x's and graph it, you will see that they intercept the x-axis, and in this case we're inverting it, so it's really the y-axis. So they will cross there at y equals -1 and 2. Again, how did I get that? You want to graph it. Okay, you can do this algebraically. It's going to probably be a little bit more difficult for you, but this would be something on the graphing part of the test where you can use your graphing calculators. So graph it, and when I graph it, again, I'm going to imagine that these are x's, so it'll cross here at -1 and here at 2, and that will be a graph that looks like this. It goes, oops, need my pen tool. It goes up and it'll come down right to here and it'll just touch the axes there. So, but again, I inverted it. So really this is my y, this is my x. Those are my two values that I end up with for my intercepts. So I've got 2 points here. This is what this means. I've got the point 2, comma, negative 1, and I've got the point 2, comma, 2. These are where my tangent lines occurred, and I need to find the slope of the tangent line there. So let's start with the first one. So at 2, 1, remember, my y prime is my dy dx, and in this case it's going to be the slope of that tangent line, so we'll call this slope 1. So at this negative 2, 1 point, I'm just going to use my equation that I had right there, and I'm going to plug in the values. So this gives me negative 1 plus 2 over 2 times negative 1. So this first slope comes out to be negative 1/2. So this is the first slope tangent. This second point, this will be m2, and in this case my second one will be 2 plus the 2 when I'm plugging into this formula from here over 2 times 2, which is 4 over 4, which is 1. This is the slope of my second tangent line. So I've got 2 of them there. Alright, let's go ahead and move on to our next problem. And this one, here's a particle motion problem. It says, suppose the motion of a particle is given by that equation, and I need to find the velocity of the particle and the acceleration function. So let's go ahead and do that. So for the velocity, I end up with s prime of t is my v of t, and taking the derivative here, it ends up being 6t squared minus 8t minus the 6, and I'm done. Now I need to find the acceleration. Well, the acceleration is just the derivative of the velocity function, and in this case I will end up with 12t minus 8. Alright, when is the particle moving to the left and moving to the right? Again, there are many different ways to do this, but I told you, let's take a look at the velocity, but let's put it on a number line. Let's simplify the problem, basically. So we know that it moves to the left when the velocity is a negative. We know that it moves to the right when the velocity is a positive. And we know that it's standing still when the velocity is 0. So let's go ahead and find out when the velocity is 0, and that'll help us determine when it's going to the left and when it's going to the right. So we set v of t equal to 0, and in this case I end up with 6t squared minus 8t minus 6. I'm going to take out a 2 here, 0 equals, and I will take out a 2, and I'll be left with 3t squared minus 4t minus 3, and my zeros end up, okay, this won't factor. If it factors, great. If it doesn't, you're going to have to do something else. So in this case, we can use the quadratic formula, or our calculators, graph it, determine what the intercepts are, and I will get 2 intercepts for this one. I get x equaling negative 0.53518, and then x also equaling 1.8685. So what are we going to do with these? We're going to put these on a number line. So here's what we're going to do. We have a velocity number line here. This is v of t, and this is going to be at 0, okay? Because I don't want a negative time. I don't need to examine anything before 0. So that starts at 0, and I'm going to put my 2 values here that I found, which is negative 0.53518 and 1. Oh wait, this is a negative value. So in this case, I don't need to use this because I don't need a negative time. So I really should have put these as t's instead of x's. Okay, and then we are going to put the 1.8685 though. So this was my time here. Again, this should just be a t. All right, so let me examine what happens in my velocity equation, which was 6t squared minus the 8t minus 6, when I'm between 0 and 1. So pick a value between 0 and 1 and put it in there. Let's pick 1. When I put 1 into this equation, I get negatives. Okay, let's put a value greater than 1.86. Let's put 2. I'll get positives. So the negatives mean velocity is going to be negative in this region and positive in that region. You can graph this and determine where it's above the axis, below the axis. Again, there are several different ways. I like using this number line method. So what this tells me is that since the velocity is negative here, we are going to the left when t is in between 0 and 1.8685. Now, I am making it equal to 0 because it's not a 0. At 0, it's a negative value, so it is moving to the left. Now, there's debates about this, but that's the way I'm going to show it here. Moving to the right, this will be when t is greater than 1.8685 because this is where the velocity is positive. So, those are the two values, or those are the intervals in which it's moving to the left and to the right. Now, when does it change direction? Well, it changes direction right here. We can see that it changes direction based on my graph right at this point. It's going backwards, and then it stops and goes forwards at that value. So this occurs at my 0, which is at t equaling 1.8685. Now we have the next question. When is it speeding up and slowing down? All right, for speeding up and slowing down, we talked about this in class, and we developed the reasoning behind this, but the bottom line, the reasoning is for slowing down, we need v of t and a of t to be opposite signs. For speeding up, we need v of t and a of t to be the same sign. Okay, so it's like if it's speeding up, you're in a car, you're going forward, and you're accelerating, it speeds you up. So there's different examples. We came up with a few in class, but that's the bottom line of how we explain that. So let's take a look at when this happens. And again, I like using the number line method. But before we do that, we need to find when a of t equals 0 so I can compare a of t. So we set our a of t equation equal to 0, and we get t equals 2/3. So here's what I'm going to do. I'm going to take my v of t, and I'm going to take my a of t, and I'm going to put these on a number line starting at 0 and comparing each. We know that this velocity changes at 1.8685, and that the acceleration is at 2/3. So I want to test a couple intervals here. I'm going to put a border here and a border there. Okay, so, well, actually, let's go ahead and before I put the borders in, let's do something. Let's walk ourselves through when the velocity and the acceleration are positive and negative. So for acceleration, we know that this is negative there and this is positive there because we solved it in the problem before. I'm sorry, for velocity. For acceleration, I can plug in a number between 0 and 2/3, and I'll end up with negatives, and then anything larger than 2/3, I will get positives. How did I get that? I used my acceleration equation, okay, and I put in a value. Put in 1, you get a positive. Put in something in between 0 and 2/3, 1/3, you'll get a negative. So now let's put in our borders here that we have talked about, and I'm going to look at and see when the acceleration and the velocity are the same sign or in different signs. Okay, so the same sign occurs right here when it is between 0, let me point to it with the pointer, between 0 and 2/3 right there, both are negatives. And then it occurs again after 1.865. Positive here and a positive there. So let's write that interval down. So same sign, so speeding up is going to happen between 0 and 2/3, and this will also occur when t is greater than 1.8685. Let's do the slowing down. This will happen when they are opposite signs, and let's take a look at our graph right here. This is a negative, these are positives. So it happens when they are opposite signs, and in this case, it's going to be between 2/3 and 1.8685. Okay, let's quickly sketch the motion of this particle. Before we do the next problem, the motion of the particle. When is it moving forward, backwards, and the position? So basically, when we sketch this, we have an s of t axis here that we're going to use. And I'll say that this is at 0. And over here is at 1. And why is that important? Well, at t equals 0, s of t is 1. And we could find that from the equation up top. We plugged it in. And at t equals 1.8685, s of t will be 11.13. Now I use these because this was from our velocity, which told us when it was moving forward or backwards. So we're going to start off here at t equals 0. We're going to move in this direction. Here's my particle motion all the way till I get to negative 11. We'll say that this is my negative 11.13 point. Okay, so we're going, and then it's going to turn around and it'll continue back going positive. So this happens at t equals 1.8685. So there is my graph of the motion of the particle. Okay, moving on to the next problem, problem 4. This is a true chain rule problem. It says, suppose we are given this f of x. I need to find when, hold on one sec, let me change the color of my pen. Okay, great, perfect. I'm given this f of x, and I need to find the derivative. That's the derivative of f of x and in terms of g prime of x. So I need to find this derivative in terms of g prime of x. So let's go ahead and do that. Well, I've got a composition here. Something's inside something. So let's write it down. We have f prime of x. So we will apply our product rule, but I have something on the inside here, and this is to the fourth. Now I have to do the chain rule here to this part, and when I take the chain rule on that part, I will get 3 times g prime of x. And cleaning all this up, I could just write this simply as f of f prime of x equals 15 g prime of x times my 3g of x, and this will be to the fourth power. Okay, moving on to the next problem. Let's take a look here. Problem number 5. Suppose we're given this situation, and we need to, it's this piecewise function. When x is greater than 2, and then when x is less than or equal to, we need to find f of x. It's continuous and differentiable. We're also told that we need to find a and b. All right. I could have left out this word continuous and said it's differentiable. And you would assume it's continuous, because if it's differentiable, it must be continuous, but if it's continuous, it doesn't have to be differentiable. We said why? Because if we have a kink in a graph, that's one example, that is something that's continuous but not differentiable. So, but if it is differentiable, then it has to be continuous. And now we need to use this concept to find a and b. So let me erase this back out, and let's work with this. So the first thing I need to do is work with the continuity. Since I know it's continuous at x equals 2, I can say that the value will be the same for this at x equals 2. And I'm going to put in my x equals 2. So this will be 2 squared plus b times 2 equals 3a 2 cubed plus 5b times 2 plus the 2. And cleaning all this up, I'm going to spare you the details here in between. You'll get 8a plus 2b on this side. And on the right side, we end up with 24a plus 10b plus 2. And I'm just going to go ahead and put my a's and b's on one side, kind of like standard form. So we'll say this is negative 2 equals 16a plus the 8b. Alright, this is the continuity part. For the differentiable part, now we can do the same thing. We know it's differentiable, so that means at x equals 2, it'll have that same value. So we can take the derivative of the first part of this, and that gives me 4ax plus b, and take the derivative of the second part of this and set them equal to each other. So this becomes equals to 9ax squared plus 5b. Again, this occurs at x equals 2. So I'll plug in that value, 4a times 2 plus b equals 9a times 2 squared plus 5b. Cleaning all this up, I'll spare you the formalities here, we end up with b equaling negative 7a. Well, what do we want to do with this? Well, we've got two equations here with two unknowns. We want to use both equations to solve for a and b. So I can go ahead and substitute in my b since I've already got it solved for. So I end up with, again, I'm going to substitute this in right there. So I will end up with negative 2 equaling 16a plus 8 times negative 7a, which ends up being negative 2 equals 16a minus 56a. So my a is going to end up being 1 over 20. Use this and solve for b by plugging it in right there, and we get b equals negative 7 over 20. Alright, almost to the finish line. Moving on to the next problem. Here we have a radius of a circle is measured with an error percentage of 0.15%. We need to estimate the percent error in the area calculation. So they gave us a 0.15% error. So this is 0.0015. This is the change in radius. This is our dr. R is a radius error. It's a change in the radius. And this will be negative on this side, 0.0015, positive on that side. Well, how does that help me? I need to find the area calculation percent error. This is a dA over A. That's what I'm looking for there. Well, let's see. I'm given that it's a circle. So I know that this is the area is going to be pi r squared. Well, that takes care of this right here. But how do I get the dA? Oh, I can just go ahead and differentiate this with respect to r. So dA equals 2 pi r dr. So I took this derivative, implicitly differentiated with respect to r. You could have said dA dr and then solved it, but I chose to keep the dr on the right side. So by doing that, now I know a dA, and all I'm going to do is substitute this dA up here. So this becomes 2, oops, I'm not sure why it kept doing that for me here. This becomes 2 pi r dr. I know what my a is. It's pi r squared. So all I did was put these two values in dA over a. So what this does is we can clean this up by getting rid of these pi's. This r goes with one of those, and I'm left with dA over a equaling 2 dr over r. But I need to get rid of this dr over r, and I need the dA over a. So let's clean this up, and we're going to say that this is 1/2 dA over a is my dr over r, and that's what I'll put in right there. So this becomes 0.0015 negative less than 1/2 dA over a less than 0.0015. Multiply everything by 2. So we're multiplying by 2, and this gives me a value on this side of, let's not skip that step. Let me go ahead and see if I can put this in. I'll squeeze this in right here. I'm multiplying everything here by 2, so this gives me 0.003 less than dA over a less than 0.003. So that means dA over a will be plus or minus 0.3%. Now, yes, some of you may have found a shortcut to do this problem, but this is how we do it, the long way, the worked out way, and explaining why it works. But again, yes, there is a shortcut to this problem, and some of you may have already figured that one out. All right, let's move on to our last problem here. This is another related rates problem. This time we've got cars, and two cars are leaving the same point at the same time. One heads north at this 60 kilometers per hour and the other east at 70 kilometers per hour. So, and after 2 hours, what is the distance between the cars? What is the distance between the cars increasing? So let's list all our givens again. I like to draw the diagram, same point, one goes north, the other goes east. The one going north, we'll call this our y, we'll call this our x. In between them, we will call this our s. The one going north is going at a rate of dy dt, that's my rate. You can again use y prime if you want, 60 kilometers per hour. My dx dt, the one that is going to the east, is 70 kilometers per hour. Again, you can use x prime if you want, I don't mind. So what happens? Well, we know after 2 hours. Let's draw what happens after 2 hours. After 2 hours, I've got this triangle again. Well, this being 140 kilometers, because I just multiplied the 70 by 2, and this being 120 kilometers, and I can use Pythagorean theorem here and solve for this s, and s will end up being the square root of 34,000. I'm going to leave it like that. I'll worry about the simplification later. What do we want to find? We want to find when the distance between the two is increasing, at what rate that's increasing. So we are looking for this ds dt right here is what we want to find. This rate, the ds dt rate. All right, let's see what we could do. Well, our basic equation that we know under our givens is the Pythagorean theorem. So x squared plus y squared equals our s squared. Okay, at this point, we want to implicitly differentiate. So we end up with 2x, x prime, which I will write as dx dt, plus 2y, y prime, which I will write as dy dt, equals 2s, s prime, which is our ds dt. Okay, so plug in everything we know. We have all our values. We have x, that's when it's 140. So x is 140. We have a dx dt. That's 70. We have a y. A y in this case is 120. And we have a dy dt, which is 60. 2, and we have our s, which is the square root of 34,000. And we are looking for our ds dt. This is the one we need to solve for. Alright, cleaning all this up, again sparing you the formalities, I will end up with 19,600 on top plus 14,400, all divided by 2 times the square root of 34,000, which will be my ds dt. Okay, let's go ahead and simplify all that down. Just go ahead and use your calculator at this point and you'll get your ds dt. You could clean it up if it was a non-calc part, but that's okay. In this case, we will end up with 29.1547. And this will be kilometers per hour, which is what we're looking for. All right. Thank you for watching. Good luck studying and good luck on your test.